6. Remember, in Chapter 6, we're talking about point estimation here. Kind of getting started with this idea of statistical inference, which sort of unlike what we've done before, is we're going to use data that we collect, or think about collecting data and using that information to draw inference or make a conclusion about something that we don't know. So we're trying to estimate a population parameter, and we're going to figure out how to use data in order to do that. So in section 6.1, we talked about just some sort of general concepts and looked at some maybe ways to evaluate estimators. We talked about unbiasedness. We talked about the mean squared error, some of those kind of things. And in many of the cases, it was very sort of easy to pick out an estimator that was good. If we were estimating the population mean, for example, we could just use the sample mean. And it had some other cases like that. It will not always be the case that it's obvious on how to estimate a particular parameter. So here in 6.2, we want to talk about some sort of general strategies or sort of widely accepted methods of finding point estimators or for doing point estimation. So the two general strategies we're going to talk about in this class, there are many more, are these two things that are listed here: the method of moments, MOM, and also we'll talk about maximum likelihood estimation later. So first, we're going to discuss this first one, this method of moments estimation. Okay, so we looked at this briefly on Wednesday. This was right at the end, so I wanted to put this up here again. Just some definitions for you, distinguishing between a population moment and a sample moment. So notice that the population moment, it's an expected value, so this is going to be, let me just make a note here, these will be a function, or these will involve the parameters, let's say that. So the expected value of x to the first power, for example, that's just the expected value, is mu, so whatever that is. That's a parameter of the expected value of x squared. You can think about that in terms of the formula that we've seen before. Again, it involves the parameters, involves sigma squared and mu. So that will always be the case. And the sample moment over here, this only involves the data. This involves. So that's going to be some function of our sample data. That's something we can calculate here. So that's the idea between distinction between population moments and sample moments. And again, these things are defined for any integer k. So you could also have the 37th population moment, for example. That would be the expected value of x to the 37th power. Or you could have the sample moment, average the observations raised to the 37th power. So that's not something you would actually probably ever use, but the point is that you could. These moments are defined for any integer power there of what we're looking at. Okay, so with that in mind, with those definitions in mind, how we'll do this method of moments estimation. Again, we want to estimate the population moments with sample moments, and we'll in fact just set those two things equal to each other. So sort of our general strategy, we'll do several examples here this morning. But if I have lowercase m parameters to estimate, so maybe if I'm looking at a gamma random variable, that's alpha and beta, so I would have two parameters. If it's a normal, I would have two parameters, mu and sigma squared. In theory, you could have as many parameters there as you want. I just need to find what those first m population moments are. Also find my first m sample moments and set those things equal to each other and solve for the parameters that I want. So yes, we'll look at some different examples of this. I think it's best illustrated probably through an example. So starting out very simple. Let's this should be a p. Let's say we have a random sample, usual setup, random sample x1 up to xn from this discrete distribution. So we have discrete random variables. So the individual samples are either 1 or 2. They're one with probability p and one with probability 1 minus p. So this is my This is my PMF here. And I want to find the moment estimator of P, the method of moments, the mom estimator of P. Okay, so kind of stepping through our usual, kind of looking back at our steps here. We first want to find what the first M population moments are and find the first M sample moments. So here I only have one parameter, right? There's just this P thing that I need to estimate. So M here is equal to 1. So I only have one parameter that I need to estimate. So this will be a little easier in this case. Okay, so my first step is I want to find the first, and I'm only looking at one now, the first population moment. So that's just, I want to find the expected value, and this will just be, you can just do this of one observation. You don't need to think about the sample mean or anything like that. So the expected value, and maybe let me make the distinction that we're raising this to the first power. So that's the first population moment. Okay. So again, this is just, we're back in chapter 3. We're finding the expected value of a discrete random variable. So this is just taking the value. The value can take on times its probability. So that's when x equals 1, that has probability p. And x can equal 2 with probability 1 minus p. And so this is 2 minus p. Is our expected value. Okay, so that's my, this is my first population moment. And note that involves the parameter that I'm trying to estimate there, right? So it's something to do with P there. Okay. Next, I want to find my general strategy here. Says now I want to find the first M sample moments. So the first, I only need to find one of these things. So this is just 1 over n times the sum of my observations of the xi's raised to the first power. So that's just our sample mean. So the first sample moment is always x bar. So this is the first sample moment, and it will always be x bar. Okay, so first 2 steps are done. M equals 1. This is a pretty easy strategy here. So let's think, what's my third step? Now I want to equate. Again, M equals 1, so I only have to do this one time. I want to equate the population and sample moments, and then I want to solve for the parameter that I'm trying to estimate. Okay, so coming over here, my third step is I want to set these two things equal. The first population moment, which is 2 minus p, and I'm going to set that equal to the first sample moment, which is x bar. So first population moment, here's my first sample moment. Okay, and I'm gonna, this is not written in the notes, but I want to get a little picky here. So in general, again, remember P is our parameter here, right? This is P is the parameter, and we don't know what the parameter is. So we're trying to come up with an estimate for it. So I feel like this statement here doesn't really make sense. We're not saying that the population proportion is somehow equal to 2 minus x bar or something like that. what we're saying is that our estimate of this parameter is going to equal, we can solve this somehow to get our estimate for the parameter. So I'm going to put a hat on the parameter there just to denote that that's our estimate and not the actual parameter, because we don't know what that is. So in that third step, I would recommend here, just being a little picky, put a hat on whatever the parameter is you're trying to estimate, just to denote that that's going to be your estimate of it and not the true thing. Just to kind of help you keep things straight. Okay, so I have that equal, and now the last step, I just need to solve this thing for the parameter estimate here. So 2 minus p hat equals x bar. Well, that just means that p hat equals 2 minus x bar. Okay, so that's my method of moments estimate there for p in this example. So p hat is the method of moments, estimator for this example. And since we're going to be talking about another type of estimation later, I might sometimes use the subscript p hat subscript mom, p hat mom. That's going to be our, just to kind of denote that that's our method of moments estimator. Okay, pretty straightforward. Nothing too crazy yet. Let's do a few more examples here. Starting out with still these sort of simple cases. So now let's kind of go back to a sort of typical example here. I have a random sample from an exponential distribution with parameter lambda, and I want to find the moment estimator of lambda. Okay, so again, I just have one parameter that I want to estimate, so m equals 1. I don't think I'll ever throw an example at you that would have m of more than 2 is fair game, but 3 would probably be getting to be a little cruel. So this can be a little easier when m is small. So the first step, I need to find the first population moment, which again is just the expected value of x. You can raise that to the first power if you want to make that distinction. So what's the expected value of a exponential random variable? 1 over lambda. Very good. Okay. My first sample moment again. Again is x bar. So that's kind of what it will always be. Again, that's just the sum, the average of the xi raised to the first power. Okay, so in my third step now, I just need to set these two things equal to each other. So I can set 1 over lambda. Let's put a hat on that to denote that that's our estimate. Set that equal to the sample moment. And then finish it off, just solve for lambda. So lambda hat equals 1 over x bar. Okay, so this is again here, this lambda hat 1 over the sample mean is my method of moments estimator. Okay, is this feeling okay with you guys? Kind of how we, sort of a constructive approach to finding estimators. You don't have to just guess at what might be a good one. Here's kind of a way of sort of an algorithm to figure out of how to find an estimator in these various cases. Okay, let's go back to this example we saw before. So again, I have going to keep doing some examples here. I have another random sample here from this discrete probability mass function that we looked at on Wednesday. And I want to think about what's the method of moments estimator of theta here. Okay. So I think we already showed, if you go back to your Wednesday notes, we showed that the first population moment, the expected value of x, we showed that was 1 minus theta over 2. This is from the Wednesday notes. But you could do that again real quick if you want to practice that. Okay. First sample moment, as usual, is just x bar. You're seeing a lot of that here. And so I come down to my third step here, and I can equate those two statements. So I have 1 minus theta, let's put a hat on it to denote that it's our estimate, is equal to x bar. And then we can solve this thing to get that theta hat is going to be equal to 2 minus 2 x bar. So this is my method of moments estimator of theta. Okay, so let's go back to a section 6.1 concept and think about because remember back in 6.1 we came up with a different estimator for theta, and so we might want to compare and contrast these two things. So what is the mean squared error of my method of moments estimator? So what is the MSE of the method of moments estimator? And again, remember from our discussion in 6.1, the mean squared error is what? Does anybody remember what that is? What our shortcut for that is?
Variance minus the bias squared.
Variance, almost. Variance plus the bias squared. Exactly right. Exactly right. Very good. So we take the variance of our estimate and we add on the bias squared. Square that thing. Okay, so let's first think about what the bias of this estimator is. The bias of the method of moments estimator. Well, that's just the bias of 2 minus 2x bar which is the expected value of 2 minus 2x bar minus theta. So you take the expected value of your estimate and subtract off the parameter that you're trying to estimate. Okay, so we can move some things around. This is 2 minus 2 times the expected value of x bar minus theta. And so we know that there's a fact here. We know that the expected value of the mean is always equal to the expected value of the individual observations. That is always true. So the expected value of x bar is the same as the expected value we found before. So this is 2 minus 2 times 1 minus theta over 2 minus theta. And lo and behold, if you work that out, that is actually, that is actually 0. So that means our estimator is unbiased here. So theta hat method of moments is unbiased. Yes, sir.
Are we going to be able to just skip straight to that since we actually found that value for the estimator? Like, shouldn't we know it's unbiased if we like equated the two, the sample mean? Yeah.
So shouldn't you know that it's unbiased because you set them equal to each other? So this will not always be the case. If you look back, will this always be the case? I think you might be right. Let me think about that. Let me think about that. Let me get back to you on that. I'm not remembering at the moment if that's always true, and I'm trying to think of an example when it's not true. Let me get back to you on that. Good question, though. Okay. All right. So this thing is unbiased. Run out of space again. Okay. Well, I'm going to erase that. So I have some space to fill out what my variance is. This thing does happen to be unbiased. So this part is 0. Think about what the variance of this thing is. So we have the variance of my method of moments estimator. It's just the variance of 2 minus 2x bar. Again, the 2 by itself doesn't matter, so this is the same as the variance of 2x bar, which is 2 squared times the variance of x bar. Which is, again, the variance of x bar is 1 over n times the variance of the individual x's. I think we already calculated that out to be 4 over n times 1 minus theta over 2 minus theta squared over 4. We calculated that. That was also from our Wednesday notes. So since I have an unbiased estimator, the MSE is just the variance. So that's 4 over n times 1 minus theta over 2 minus theta squared over 4. Okay, so yeah, so when you have an unbiased estimator, your MSE is just the variance. Okay, so we could use this again. Remember, the mean squared error is one of our criterion. So if I ask you a question, which one do I prefer, my method of moments estimator or just the regular x bar estimator that we found back in section 6.1? If I ask you which estimator you prefer of two, there are two criteria that you can use. So the first one is, I guess let's just say unbiasedness is the first one. So you might, again, remember our discussion, you might be inclined to choose the unbiased estimator. But our sort of secondary criterion is to look at the MSE, which has smaller mean squared error. Okay, so if I want to compare between these two estimators, yes, I can look at their mean squared error and their biasedness. And I guess what we found was that the first estimator was biased, right? So this thing was indeed biased. So if that's a big concern for you, then maybe right off the bat you could choose the other one. But just to do a quick comparison of the mean squared error, remember the MSE of my first estimator was that thing there. So we found that on Wednesday, and the mean squared error of the method of moments estimators, that's what we just found there. And so you want to try to compare these two things and say which one of these, which estimator gives me a smaller mean squared error. And it's not always easy to directly make that comparison, because the thing depends on, so the theta is in there, and I don't know what theta is, so it's hard to say exactly which one of these is smaller. This plot that I have in your notes here, is I've actually plotted the mean squared error as a function of n. So down here is my sample size n, and here's my mean squared error. This can be a good way to look at these things. So this red line here, this is the mean squared error for the method of moments, and this black line over here is the MSE of just the first estimate that we found. And so if you were actually doing this estimate, you might want to wait and see what your sample size is. So if you have a large sample size, then the method of moments estimate is going to be better. Smaller sample size might not be as good. So which one do we prefer? It depends on the sample size. So for small n, so if n is less than about 35, we might go with theta hat has smaller MSE, and for large n, the method of moments has smaller MSE. Okay, so again, the key thing comes down to comparing the mean squared errors here. Sometimes that will be a little more obvious of how to sort of directly compare those two things. Here it's not at all obvious, so we can plot the mean squared error and use that to sort of see which one is smaller. That's just as good. But okay, but the main point of this last part of this example is that if I ask you to choose between two estimators, here's your two criteria. So you can either talk about which one is biased or which one is unbiased. If they both happen to be unbiased, then you definitely want to use the mean squared error as a criterion. So look at which one has smaller MSE. Those are your two ways of choosing between estimators. Okay, so enough of these one-dimensional parameters. Let's try a two-dimensional parameter. So if few more examples of this. If I have a random sample from a normal mu sigma squared distribution, what are my method of moments estimators of mu and sigma? Okay, so again, back to our usual strategy here. First, we want to find the two. We want to find the, so now m equals 2, right? We have both mu and sigma squared. So I need to find two population moments now. So the first population moment is just the expected value, so that's just mu. The second population moment, that's expected value of x squared. And I guess in general, you could calculate that directly, but to save ourselves some time, again, we can use a shortcut that this is the variance of x plus the mean of x squared. It comes from that shortcut formula for the variance that we have. So then the second population moment is sigma squared plus mu squared. So I think we saw that previously on a slide. Okay, so there's my, yes sir.
Could you find any other ways since you don't really have like any sample data?
Say that again?
Could you find the expected value squared, like e of x squared? Could you find that since you don't really have any other sample data, or would you have to use a shortcut?
No, you could calculate that directly. So that would just be the expected value of x squared. Well, that's just, again, remember the integral from negative infinity to plus infinity of x squared times your PDF. All right, so here your PDF is some, well, I think I put the formula for the normal PDF up there. It's not something you would want to actually do. Yeah, so that's always a fine way to do these, to calculate that expected value. You'll be able to do that, but you will save yourself a lot of time if you can use sort of shortcuts like this.
Okay.
But welcome to do it that way as well, absolutely. Okay, so now let's write down what our first two sample moments are. So the first sample moment, again, that's just x bar as always. The second sample moment, this is 1 over n. This is an average of the squared observations. Okay, so we don't have an abbreviation for that, so we'll just leave that as it is. Okay, so now we just need to, let's do these steps together. We just need to set these things equal to each other and solve. So I have two equations. I'm going to set the first population moment, which is mu hat, set that equal to the first sample moment. That's x bar. So there we go. We're done. And then I also need to set the second population moment, sigma squared plus mu squared. Put hats on those to denote estimates, and set that equal to the second sample moment. Okay, so then so mu hat's already solved for, so sigma hat squared. Figure out what that is. Well, that's just going to be 1 over n. It's my second sample moment, and then I can subtract off mu hat squared, which I know is x bar squared. So since I already know what mu hat is there, I can just plug that into the second equation. And a little wonder of algebra here, that in this case this is actually equal to this squared difference between the observations and their mean. So if you want to work that out, that is in fact true. Okay, so if you kind of recognizing this is equal to, remember the sample variance S squared was 1 over n minus 1 times this sum. So my method of moments estimator down here is equal to n over n minus 1 times the sample variance. Or sorry, other way around. Well, let me just write this out. So this is equal to n minus 1 over n times 1 over n which is n minus 1 over n times the sample variance. Sorry. So this should be a n minus 1 here. Okay, so the method of moments estimator there is a function of my sample variance.
If that's n minus 1, don't they just cancel?
What's that?
The blue thing you just corrected, doesn't that just cancel with the numerator?
Yes, exactly. So this thing that I did a typo on, this is my, so yeah, they do cancel, but it's, so the first thing we wrote out there is fine, just to denote that, just to point out that it's almost the sample variance. Yeah, so just kind of drawing that connection there between the thing that we saw before, the unbiased estimate there. So here's a good example of the earlier discussion. So the method of moments estimated are not always unbiased. So here's this is sigma hat squared method of moments is actually biased. So I think what you said would have been true when you just have one parameter. So if you just have when m equals 1, the method of moments estimator is unbiased. But remember, S squared was our unbiased estimator, and this method of moments is not quite that. So this thing will be biased. Questions, comments? Is this feeling okay? Kind of what we're doing aside from all my writing errors up here. Okay. Well, at the risk of boring you, I want to do one more example, something a little different that we haven't seen before, before we move on to maximum likelihood estimation. Okay, so throwing something that's a little different at you here. Let's say I have a random sample now from this distribution here. So this is a continuous random variable, and it's actually called, it has a name. It's called the shifted exponential PDF. So it's, you can sort of look at the form of that and think I'm just shifting. Instead of starting at 0, I'm now starting at theta and going off to infinity. So now I want to obtain the method of moments estimators here of theta and lambda. So I have m equals 2. I have 2 parameters that I need to find here. Okay, so the first, I need to find the population moments, so the expected value of x. That's integral from theta up to infinity of lambda times e to the negative lambda x minus theta. Okay. So I can do a little substitution here. Let's let u equal x minus theta. so that du equals just dx. Sorry, I have another mistake here. So there should be an x in front of there. Sorry about that. Okay, so if u equals x minus theta, x equals u plus theta. So this is equal to the integral, and now my endpoints shift from theta to infinity to just 0 to infinity. And I have here a u plus theta times lambda e to the negative lambda u. Du. Okay, and the theta comes out since it's a PDF that integrates to 1, and I just have the expected value here essentially. That just looks like an exponential. Having a little trouble writing today. This is an exponential random variable with parameter lambda. So this is just theta plus the expected value of an exponential, which is 1 over lambda. Yes.
Why could you pull out the theta, like the theta plus, then the integral? Why do that?
Yeah. So here, what I could have written out this out is the integral from 0 to infinity of let's pull the theta out front. Times lambda e to the negative lambda u du plus this other expected value, so u times lambda, and then this thing is a PDF, so that just equals 1. Yeah, good question. Should have made that more clear. And then yeah, just the point is that I recognize this as an exponential random variable, the other part, so I can just say that that's, I don't need to actually do that calculation again. Could if you want to, but no need for that. Okay. And similarly, I can show that the expected value of x squared, I'm not going to work that out in here. If you want to try that on your own, go for it. That'll be theta squared plus 2 theta over lambda plus 2 over lambda squared. So if Matt, if you're feeling like you want to try some extra calculus, you can check that that's right. Okay, so those are my population moments, my sample moments. Those are going to be the same as before. So I have x bar and the average of my squared observations. And now I just need to set these things equal to each other. So my third step here, I have this system of equations. I want to set 1 over lambda hat plus theta hat equal to x bar. And I have this other equation, so theta hat squared plus 2 theta hat over lambda hat plus 2 over lambda hat squared. Set that equal to this second sample moment. Okay, and so I have two equations and two unknowns. So I can solve for each one of those things. It's not too bad. There'll be some little algebra there. I'm going to forego actually writing through all the calculations of how we solve this. But I can solve those two things to get my method of moments estimators. So my lambda hat is going to be equal to 1 over square root of second population moment, second sample moment rather, minus the mean squared. And theta hat will be x bar minus the same sum there. So so if you're feeling bored and want to do some algebra later today, you can check that that one works out like that. Okay, so this is to point out that these things can be a little trickier here than those simple examples we looked at first. Okay, so just to kind of bring this back to some actual real data here. Suppose now that suppose you're doing a sample where you're taking samples from this distribution, and I've taken 10 observations and I get the following values. So there's 10 numbers there, and from that I want to actually figure out what my estimates of theta and lambda are. So if using these 10 numbers, my sample mean is 1/10 plus 3.11 plus all 10 of those numbers, and that is 5.58. In my second sample moment, I can calculate that. That's the sum. That's the average of these squared observations. Well, those are of my individual xi squared. If you do that for those 10 numbers, that's 56.97. So here n is 10. So just point out that I can actually calculate those. Once I have data, I can actually calculate what those things are. So then my estimates will become lambda hat. Again, remember was 1 over that's second sample moment minus the first one squared, so 56.97 minus 5.58 squared, which is 0.1967. And the estimate for theta is x bar minus that same denominator, so 56.97 minus that's 5.58, and that is 0.497. Okay, so just to point out that after I've done all that work to figure out what the estimators are, once I actually have data, I can just plug that data in, and here are my estimates. So If you were in a setting where you were trying to estimate the parameters of this distribution here, there's one way that we could do that. So our estimates for lambda is 1.1967. My estimate for theta is 0.497. So just to note that we can actually calculate these things out if I have data. Yeah, Jamie.
So what does this tell us about? I mean, it seems like we're just calculating numbers, but I don't really understand what it's telling you.
So yeah, so what are we doing here?
Yeah.
What are we doing here, right? Well, so I think coming back here to this normal example, we sort of have intuitive ways of estimating what our parameters are. So I guess the overall point of interest is that we want to be able to say, I don't know what the parameters are, right? I don't know what mu and sigma squared are, for example, in this example. So how can I use, sort of what's a good way of using data to give a good estimate for what those things are?
It seems like we knew the curve, then found data to fit the curve, which seems backwards to me.
Right. So yeah, so we're assuming that our data has a normal distribution, for example, and that's a big assumption, and we're not going to talk about that for now. We'll just suppose that it is. So we know what the shape of our distribution of our data sort of looks like. So you could imagine that you have no other information, but you might think it reasonable to assume that it has a normal distribution. So I know what the shape is, but I don't know where it's centered, and I don't know how spread out it is. So I guess you just have to sort of accept that we're making a distributional assumption, which is a big assumption. There are statistical methods that you don't have to make those assumptions. It's called non-parametric statistics, which we won't talk about in this class. But anyway, so we're making an assumption about the distribution of what our data is, and then we want to use that data to estimate what the parameters are. So I think in this normal case, it's maybe sort of obvious. Well, I'll just use my sample mean and my sample variance or something close to it. But for this distribution here, it's a little less obvious as to what's a good estimate for theta, what's a good estimate for lambda. So just kind of trying to construct a way of using our sort of constructive methods to figure out what a good estimate for those parameters are. Is that? Yeah, so there is still a lot of assumptions going on here. But isn't that all of science, I guess? Would be the lesson of the day. I don't know. That's a good question, though. Okay, well, if there are no other questions, this is a good place to stop. Thank you guys for being here. Have a wonderful weekend, and we'll see you next week. Great question. Let me stop this real quick.